So let's begin our discussion with deformation of solids. So initially, when we're talking about deformation of solid, we're going to focus on two things. We're going to focus on stress and strain. At the same time, we're going to focus on elastic and elasticity behavior. So in general, we're going to focus on the spring, which is under also we can say it is also under Hooke's law. Okay. So one thing that we need to know is that I'll first introduce Hooke's law, where we say Hooke's law states that the resultant force is direct proportion to the displacement. What does it mean? If we have got a spring and then we are trying to stretch the spring, it is possible that I can stretch that spring, reaching at the maximum position. At the same time, if I exceed the maximum position, I'm going to reach at a state where when I leave it, the spring will not go back to its original position. Again, if I go beyond that state, I'll reach at a state where the spring is going to break into two parts. So there are two things which you have to know. There's a part which obeys Hooke's law, which is linear part. Then there's a part which we call it a plastic limit. Let me just give you this. Before I explain this, let me first explain about stress. So what is stress? Basically, when you hear the word stress, it is the same stress, you know. I'm stressed. You have got a lot of work at a very short period of time. So you are stressed. That is the same stress we're talking about. So when we're talking about stress, it's the same as pressure. I have got pressure. I need to study this. I need to do this. I've got this work within a short period of time. At the end of the day, you're going to have pressure. So pressure is the same as stress. When someone is talking about stress, this is the same as pressure. And we do know that pressure is given by force divided by area. Okay? Meaning that even stress is given by the same formula. Stress is given by the force divided by area. Like that. So initially when we're talking about the stress and pressure, basically we're talking about the same thing. Okay? So we know that force, the SI unit is Newton, area is meter squared. So we can say that stress, the SI unit is Newton per square meter. Like that. Now one thing we have to understand is that if we have so stress and strain happen at the same time. What I mean is this. If I've got a wire, if this is my wire, I wanted to do an experiment for you, but I don't have the spring. If I'll manage to find the spring next time, tomorrow I'm going to use I'll give you a very simple experiment. If this is my wire, okay, so I'm applying a force in this direction. I'm trying to stretch the wire. Definitely the length now, this length from this point here all the way to that point is what we are going to call L initial, meaning is the length initial. So if I apply the force, I expect this wire to go maybe all the way to that point. Okay? Meaning that this now, from that point all the way to that point is what I'm going to call L final, meaning the length final. Okay? So I can clearly see that this part here from this point here all the way to that point, that is going to be my change in length. That is how much change in length I have. That one. Now, how do you find the change in length? The change in length can be found by the L final minus L initial, like that. One thing we need to understand here now is that when we're talking about the change in L, okay, we are talking about the extension. If you hear any question talking about find the extension, they are asking about the change in L. But you never have a question where when they ask you to find the change in L, you use this formula. No. They will not even give you the final length. But there's another formula which I'm going to introduce which you have to know. Okay? Sometimes this thing can be placed as this. We put it like this, the wire is like that, and then we include the load. Anything which is going to be attached to this wire, which is going to make this wire to be stretched, that is what we call the load. So it can be the force. The force we can call it load. That is just okay. Okay? Then again, one thing you have to understand now is that I said we want first to talk about the stress and strain. These two things happen at the same time. The force that you are applying to stretch the wire divided by the area is what I said is what is the stress. So I gave you this formula to say stress is given by the force divided by area. Now, there is what we call strain. Strain is just basically the change in L, the change in length divided by the length original. So we are not interested in the final length. We are only interested in the change in L divided by the L initial. So if I have got the L initial, I also have my change in L, then I can be able to find the change in L using strain. So strain is given by change in L divided by what? L initial. Now this L0 is what we call the length initial or initial length. Then this change in L is what we call extension. If you see any question asking about extension, they are asking about this change in L. At the same time, in some other books, they will tell you to say this change in L is also known as elongation. Okay? So if they also ask you about elongation and change in L, we are still talking about the same thing. So elongation, extension, and the change in length. Basically, we're talking about the same things. Is that okay? Okay. Now, what we need to understand now is that if I have got this, okay, so I'm going to have this, and then from this part here, I'll say it goes like that, then it goes like that. So I'm going to call this part to be point A, that part to be point B, that part to be point C, then that part to be D, like that. Now, we said that Hooke's law obeys this formula. The resultant force is equal to negative kx. I'll explain more on the negative part, or I'll explain more on this formula. But for now, let me just give you that the Hooke's law is equal to the force is given by kx, like that for now. So from point A all the way to point B, this point is what we call it obeys Hooke's law. Hooke's law only obeys when it is linear. From point A to B, that is only Hooke's law. That point is what we call elastic limit. Is that okay? Yes, so from point A to B is what we call from point A to B is what we call the elastic limit. I'm going to explain. Then from point B to C, this is what we call plastic limit. plastic, or let me just put, I write this plastic here, plastic limit, like that. Then point C to D is what we call breaking point. Breaking point. But let me explain more. Now, here we are going to have the force in this. Now, the force is in Newton. Here we are going to have what we call um we're going to have what we call extension, which is the same what? X in that case. So here we have extension, which I've told you that is the same as the change in L. Okay? So you can take any from point A to B. The value of K, you can get any point is going to be the same. So that part obeys what? Hooke's law. So you can get this point here, you get the gradient, the K value. When you find the gradient is equal to the K value. And you know to say, finding the gradient in this case, if I've got x and y axis, or x and y axis, you say the gradient is given by the change in force divided by the change in extension. So this one will be now x, the displacement, the change in extension. When you find that, that is going to be okay. So if you have been given any graph which there is a force and the distance, and then they want you to find the value of k, you just get any point, 2 points, the change in f and the change in x. The answer you're going to find, if you get the gradient, that is the value of k. Okay? So now, what is elastic limit? Elastic limit, it is a point where when you stretch the spring, you are going to reach at the maximum point, whereby when you leave it, it will come back to its original position. The best example I can give you is this one. If this is my spring, if I'm stretching this spring all the way at that point, if this is my elastic limit, I've reached at the elastic limit, meaning once I leave this, if this is at equilibrium position where x is equal to 0, this spring will come back to its original position once I leave it, meaning I reached at the elastic limit. There is a point where when you stretch the spring, when you leave it, it will not go back to its original position. At that point, we say you have reached at plastic limit. You know, when we're talking about plastic, if you get any plastic, you stretch it, it can't go back to its normal size, right? You know that, right? Exactly. It can't go to its normal size. Now, at that point, the moment you stretch the spring, it can't go back to its original position. You have reached at the plastic limit. Beyond plastic limit is what we call breaking point. The spring is going to break into two parts. Is that cool? When you stretch the spring, you reach at the maximum point, we call it elastic limit. You go beyond the elastic limit, you reach at plastic limit. You go beyond plastic limit, you reach at breaking point. Once you reach at breaking point, the spring is going to break into two parts. That is very, very, very important. Now, one thing we have to understand, sometimes we need to also know that we can also calculate work when you've been given the graph like this. Okay? So this graph, if you can see, in x-axis I have got the displacement. Extension is the displacement. In y-axis I've got the force. I want you to understand there. In x-axis I've got what? The displacement. In y-axis I've got the force. And I want to find the work. Finding the work, it is just the same as finding the area under the curve. So work will be equal to the area under the curve. What does it mean? If I want to find the area at this curve, meaning this is my shape. What shape is this? The one which I've just highlighted in yellow. Yes, triangle. Now, what is the area of the triangle? So the area of the triangle is given by half BH. Now, one thing you have to understand is that this B is the breadth here, or I can say the base, which is X, not so. The H is the force, the height here, in this axis, Y axis. So meaning that area will be given by half, okay? Then I have got the B is X, the height is force. I can rearrange this and say area will be equal to half F times X before I continue from here. Any question? Now, one thing we also need to understand is that the force is given by, from semester 1, the force is given by, this one force is given by what? By Kx. Yes. So I'm going to replace Kx with where there is force. So I'll say my area will be equal to, remember in this case I don't know the force. So I'll say it is half Kx, again there is another x outside. Meaning area is equal to half Kx times x is going to be x squared. Perhaps you have seen this formula, since I'm saying that area is equal to the work is equal to the area under the curve, meaning that I can replace where there is area with the work. So perhaps you have seen this formula somewhere. I know you have seen this formula. And this is the first question in your tutorial sheet where they ask to say, show that the energy, the work done by the spring is given by half Kx squared. This is how you show it. It's simple, right? Now, another thing which you have to know under deformation of solid is, since for Hooke's law we have already talked about that. Now let's talk more about the K. We are saying that F is equal to Kx. So X is the displacement, that one we know already. K is the spring constant. Spring constant, like that. Then the F is the force applied. Okay. Now K, if we use dimension analysis, I will not waste time to do that, but the SI unit for K is Newton per meter. That is one thing we need to know. And then another thing which you have to understand under deformation of solid is what we call the Young's modulus. Now I mentioned something like, we have talked about stress. Let me just write it here. It is a force divided by area. Then I've also mentioned about strain. I said it is the extension, which is change in L, divided by L initial. Now in some books they will tell you to say strain is represented by, should I tell you this? They will tell you to say strain is represented by, just like this, more like it's E, but the type of E is like the way I've written it, like that. Then this change in L, the change in L, they write it as E. But even if you put it like this, no one is going to penalize you. I think this is the best. This is the best. Okay. So if maybe you're going to be going through notes and then you find that they give you this. This one simply means strain. This one simply means change in L, or elongation, meaning E. And for sure here we know that this is in meters, this is also in meters. Meters and meters can go. So strain has got no units. Okay. Yes. Now, also another thing which you need to know is that um there's what we call Young's modulus. In some books, there's what we call Young's Young's modulus. This is the last part of um, this deformation of solid. So Young's modulus, one thing we need to know is that Young's modulus, in some books, they'll tell you to say it is just the y m. Then in some books, they'll tell you to say it is represented by capital E, like that. But in most cases, they represent Young's modulus with capital E, like that. So Young's modulus is given by, so I'm going to use what they like using, which is E, which is E. Young's modulus is given by stress divided by strain. Okay? Do you understand the fact that we said that stress is given by force divided by area? Again, we said that strain is given by, I've even forgotten, the change in L divided by the L initial. So this Young's modulus then is going to be the force divided by area divided by strain. Strain is the change in L divided by L initial, like that. Do you understand the fact that this is the same as F over M divided by the change in L over L initial? It's the same, right? So I'll say F over M times the change in L over the change, or L initial over this. I think that one you know. The next thing which I'm going to do is my final formula for Young's modulus will be equal to the F times this divided by the area times change in L. So this formula is very, very important. Test 1, this is coming. And then one thing you need to know is that area, most of the times, if you have not been given area, they will give you maybe more like a wire. If they're asking about the wire, they will give you the radius. So to find the area is going to be given by pi r squared, always in that case. Is that okay? So this is what you need to know under deformation of solid. Now let me first talk more about the K value. So we are saying that K is a spring constant. Spring constant. So if K is spring constant, so K tells us how stiffness or loose the spring is or the material is. If the K is greater, if the K value is greater, then we are dealing with a stiff material. If the K value is less, we are dealing with loose material or the spring.